On occasion, you'll be asked to simplify or provide an answer in simplest radical form. Okay, and a radical is this funny symbol here that's around the 9. It's also called a square root. So the two are similar. So we need to discuss what is squaring and what is taking the square root. Each is the inverse or the opposite of the other. So when we have 3 to the second power, we call that 3 squared, because that's the same as saying 3 times 3, and that does equal 9. And if you notice, if I have 3 units by 3 units, I do create a geometric square that is equal on all sides. So that's why we call 3 to the second power, why we call it 3 squared. Okay. Now, the opposite of squaring a number is to take the square root. So if you notice here, if I take the square root of the 9, which is the number of units in my square, the square root of that is 3, because 3 times 3 is 9. So anytime we have this square root in the 9, it's the question it's being asked is what number times itself will give me 9. Okay, and it is 3, because 3 times 3 is 9. So this is what we call a perfect square. Okay, 9 is a perfect square because it creates a perfect square. Because 3 across and 3 down will create a geometric figure that's equal on all sides. So when we are asked to put an answer in simplest, what we call simplest radical form, what we want to do is factor out as many perfect squares as we possibly can. And it's very similar to a factor tree that you've done previously. So here I have the square root of 28. So the first thing I want to do is I want to factor or come up with 2 numbers that will multiply to 28. And ideally, if we can think of a perfect square that will multiply to 28, it makes our job a little bit easier. And you'll see here that 4 times 7 equals 28. Now, the square root of 4 is 2, because 2 times 2, or 2 squared, does give me 4. So that does equal 2. And you'll notice here that the square root of 7, that doesn't create a perfect square. There is, as a matter of fact, 7 is prime. So the only 2 numbers that multiply to 7 and 1, the only 2 numbers that multiply to 7 are 7 and 1. So because there isn't a number times itself, I should say there isn't a whole number that when I multiply it by itself I get 7, I leave 7 in underneath. I keep that underneath that radical sign. So when I say we want to factor out as many perfect squares as we can, this is what I'm talking about. 4 is a perfect square because 2 times 2 equals 4. So that any perfect square whole numbers we can get, we put on the outside of the radical sign, and anything that doesn't stays inside. Let's take a look at our next example. Here we have 60. Now, off the top of my head, I can't think of a perfect square that divides into 60 evenly. And just to clarify, let me list what those when I refer to a perfect square, I'm looking for those numbers that give me this example here. That those units, those number of units create a perfect geometric square. Okay, and that of course is going to be 1, because 1 times 1 is 1. It's going to be 4, because 2 times 2 is 4. 9, 16, 25, 36, 49, 64, 81, 100. So these are our perfect squares 1 through 10. This is 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, and so on. Okay, so looking at my perfect squares list, I can't think of any that divide evenly. So I can just choose 2 numbers that multiply to 6 and 10 and work my way down. So I know obviously that 6 times 10 equals 60. So from there, I'm going to factor 6 into 2 and 3 and 10 into 2 and 5. Now you notice, because this is a multiplication, I can rearrange the numbers. And you'll notice here that I have a pair of 2's. And those pair of 2's are the same as the square root of 4, and I already know that the square root of 4 is 2. So the one perfect square that's divisible by 60, or that I can factor out of 60, is 4, which square root of 4 is 2. And that just leaves me with what I have remaining, which is 3 and 5. And 3 and 5 are both prime numbers and cannot be factored. So we can just multiply those together and get 15, because I can't factor them any farther. So my final answer would be 2 square root 15. Okay, so let's take a look at number 3, square root 18. Now the square root of 18 I can do 2 different ways. The first is, well, I know 9 is a perfect square, because 3 times 3 is 9, and 9 times 2 will give me 18. So square root of 9 is 3, and the square root of 2, there's no whole number value that will give me the square root of 2 that isn't a decimal. So this is my final answer here. But if you didn't remember 9 times 2, maybe you use 6 times 3. Okay, well that's okay too, because when I factor 6, I get square root of 2 times the square root of 3. Ah, okay. Well, if you notice here, I have a pair of 3's, which is the same as the square root of 9. So that's my whole number, 3, for my pair of 3's, and then leaving me with just the square root of 2 that wasn't accounted for. So either way, you get the same answer. It doesn't matter which approach you take. And of course, 24, there's a couple different ways we can do that one. We've got 4 and 6. That's the shortest, because 4 is the perfect square. But I could also do 8 and 3, or I could do 12 and 2. Any way you approach this, The 4 and 6 is going to be the shortest because the square root of 4 is 2, and the square root of 6 we know is prime. But with the 8, I could factor out the square root of 4 and the square root of 2, leaving me with square root of 4 being 2, and then that just leaves me with square root of 2 times the square root of 3, which we already know is prime. Or here we could do 6 and 2, or even 4 and 3. And again, we get the same answer. So regardless of your approach, you will get the same answer each time. Check out the second page and give these problems a try.